In this video, we're going to carefully go through one of the most important definitions that we will have for the entire semester, and that is the definition of convergent sequence. The definition given in our book is shown. You should definitely stop the video and copy this definition down carefully in your notes, and then start the video back up. When we look at this definition, we see that the sequence converges to X if and only if, because it's a definition, any open interval. That is a universal quantifier, which is often written as an upside down A. Any open interval containing X, there exists. Well, that is another piece of logic. That is the backwards E quantifier, the existential quantifier. Such that, and then we have an implication. So we can rewrite this definition in a more symbolic way as saying that our sequence converges to X if and only if for every open interval S that contains X, there exists a capital N inside the natural numbers such that if N is bigger than or equal to capital N, the nth term of the sequence belongs to S. Now, the first thing that I want to do is I want to illustrate what this particular definition means for a particular open interval. So if we have an open interval that contains X being given, then what this definition means is the following. If we take a number line, and here is X on this number line, and here is our open interval S, this particular definition is saying that once I get past capital N, or up to capital N, the terms of the sequence have to be inside my open interval. So Pn might be there. Pn plus 1 might be here. Pn plus 2 might be here. Pn plus 3 might be here. And then we hop back here for Pn plus 4, and so on. But the point is that if little n is bigger than capital N, Pn belongs to this particular open interval. Now, there's another way of thinking about this. What this is really saying is that the whole tail, this says the end tail of my sequence is a subset of the open interval. Remember that the end tail is the sequence Pn as n goes from capital N out to infinity. And this end tail very clearly has to be a subset of my open interval. Now, the point of the quantifier, the universal quantifier, so I want to kind of go back up here. The purpose of this quantifier here is that no matter what S I pick, I can still find some tail that will belong to it. And I want to write that down in English on the next page. So what our definition is really saying is that the sequence of the PKs will converge to X if no matter what teeny tiny interval we pick, so no matter what tiny open interval we pick, we can always find a tail that is a subset of our tiny little open interval. Now, the easiest way of thinking about tiny little open intervals is to be thinking in terms of delta balls. In other words, if this is x and I let delta be bigger than 0 be a tiny number, so I get a little tiny epsilon ball. So this is my epsilon ball centered at x. Then there's going to have to be an entail that is a subset of that delta ball. But then I can think in terms of a smaller delta ball. So now let delta hat be even smaller than delta. So this red one is my delta hat ball. We can still find, it's a new entail, but we can still find a tail. Let's call this one an M-tail, such that the whole tail is a subset of this tiny little epsilon ball. And typically in this kind of a situation, what we would be expecting is that the M tail, the M is going to be bigger than or equal to the N when the delta hat is smaller than the delta. In other words, the smaller I make the delta ball, let's get another color here. The smaller the delta ball, the further out in the tail we have to go to trap the tail inside the delta ball. So let's get that written down. The smaller the delta for the delta ball, the further out we have to go to get the tail trapped inside our delta ball. And so that's the trick that we have to be able to do when we're trying to prove something is convergent. We have to be thinking in terms of teeny tiny little arbitrary delta balls and figure out how far out in the tail we have to go in order to trap all of the terms in the tail inside the delta ball. We will see an example of that in a later video when we look at an example of proving convergence.